Io is Jupiter's closest moon, radiation-soaked and tidally racked, and so volcanic it blows material clear into space itself. Visiting there would seem crazy and reckless. So let's go colonize it instead. Over the years, we've looked at settling most of the planets in our solar system, as well as the asteroid belt, the Kuiper belt, and even some of the larger moons like Titan and Ganymede, and of course our own moon. But perhaps one of the most valuable yet tricky places to settle will be Jupiter's moon Io, since its surface is anything but settled. Io, the closest of Jupiter's big four Galilean moons, orbits Jupiter every 42 hours, which amounts to its day length too, as it is tidally locked, like most moons. It's 5% wider than our moon and 3% denser, resulting in 21% more mass than our moon. It's considerably denser than the other Galilean moons, twice what Ganymede and Callisto are, and a quarter more than Europa, the next closest of the four to Jupiter. The reason is not too hard to guess. Those bigger moons in the outer solar system contain a lot of ices. Water ice, ammonia, and methane are very abundant out there where it's cold enough for them to exist as solids. They are a lot less dense than the rocks and metals of bodies in the inner solar system, but Io is spinning fast and close to Jupiter, and thus is under constant tidal forces shoving it around and heating it up. Io is the most volcanically active body in the solar system, with over 400 active volcanoes. This activity is driven by tidal heating caused by gravitational interactions with Jupiter, and also its neighboring moons, Europa and Ganymede, the most massive moon in the solar system, and which we discussed colonizing earlier this year. These forces create friction in Io's interior, generating heat that powers continuous volcanic eruptions. This means it's not the most stable place to settle, but also means its surface is covered with sulfur and sulfur dioxide, resulting in vibrant colors ranging from yellow and red to black and green. The landscape includes vast plains of solidified lava, sulfur lakes, and towering volcanic mountains. Needless to say, it would be an interesting place to visit, but it also represents a vast treasure trove of resources. Ironic in a way, since Io is sandwiched between the biggest moon in the solar system and the biggest planet. Indeed, Jupiter outmasses everything else in the solar system combined except the Sun, and yet Io is probably the easiest to get construction material for this region of the solar system. To be fair, there are many more moons of Jupiter that are merely captured asteroids and could be easily mined, but Io likely has an accessible abundance of virtually everything, and a ready power supply the others lack, far from the Sun. Volcanic activity also gives you veins of ores that asteroids may lack. We also need to acknowledge some cons. First, while doubtless abundant in many elements, the surface is covered in sulfur compounds from constant eruptions, so you probably need to dig. Which is okay because the surface of Io is not a pleasant place. We often joke on the show that Venus is a suburb of hell, given its extreme temperature and clouds of sulfuric acid. But if Venus is a suburb of hell, then Io is an established neighborhood. Indeed, it's a bit ironic that we have a ton of other dwarf planets and moons named for underworld deities, but the places most worthy of the title, Venus and Io, are both mythological figures noted for their beauty. Venus, Jupiter's daughter and the goddess of love, and Io, one of Zeus or Jupiter's most well-known lovers. Io, in short, is a radiation-saturated volcanic landscape, and we can't really dig in because it's got all those earthquakes and volcanoes, right? Kind of. I suppose they could be called Io-quakes instead of earthquakes, but let's keep to what we know. Io is racked by a massive gravitational tug-of-war. Indeed, while on Earth we see the oceans rise and fall with the tides, but the Earth and sky do too, and on Earth the ground moves a bit under a foot up or down with the tide, whereas on Io the ground tide is more like 200 to 300 feet up and down. Those volcanoes can also blast material a couple hundred miles into space, and this is presumably part of why it has a higher density than its three Galilean siblings. It's blowing lighter material up, where some of it gets lost. The lower gravity helps. Io's gravity is 11% higher than the Moon's. but still only 18.3% of Earth normal. That lower gravity also makes those quakes safer than an equivalent one on Earth, but we don't really get that degree of stretching. I'm reluctant to say we couldn't build on Io's surface or under it safely, but those quakes are problematic. I think you might be fine operating vehicles down there. Think large rovers or snowmobiles, only over a snow of sulfur dioxide. It's also hard to emphasize enough how radiation-soaked that surface is. Indeed, Io's red-brown polar region is a product of sulfur dioxide frost being pounded by radiation. We also expect little to no water there, having been blown out by volcanism in the distant past, though given the proximity of water-rich Europa, this is probably not a big concern. We would not expect to find life on Io, though its volcanoes offer an energy source for organisms akin to deep-sea hydrothermal vents that are the lead candidate for the origin of life on Earth. We'll be discussing the idea of life on such planets or moons more in our next episode, Fungal Aliens, coming out October 13th, 2024, this month's Sci-Fi Sunday episode. While we'll talk about ways to actually live on Io or even terraform it later, a point we made in some of our other colonization videos is that colonizing a place is not the same as actually living on it, and while its surface might be a bit rough, the orbital space around it is just fine, so you might opt to live in orbital habitats. Getting back and forth with people and cargo could be done by rocket. The gravity is low, and there's no shortage of propellants or fuel in the Jupiter area, but this might be an ideal place for a skyhook or rotavator. Since Io has no atmosphere of note, we don't really have to worry about how low a habitat can be, but even if you decide to suspend collectors into those volcanic plumes, which we might, you have a lot more gravitational perturbation on lower orbits, especially with a moon that might be described as a big ball of jello wobbling around. 100 miles or 160 kilometers above Io's surface, your orbital period for a circle would be 2 hours long and have a tangential velocity of 1.73 kilometers per second, just over a mile per second, so that you would complete 12 orbits an Earth day and 21 for an Io day or year. This might be a bit low, and even up 500 miles or 800 kilometers above Io's heaving surface, your orbital period is still 3 hours, with a tangential velocity of 1.51 kilometers per second, just under a mile per second. Here you would complete 8 orbits in Earth day, or 13 an Io day or year. My guess is that you are placing your orbitals somewhere between those two, and possibly on an elliptical orbit. We'll assume a space hab here. It could be big or small, but let's say it's a cylinder habitat called Apathis, Io's son by Zeus and the king of Egypt. Many people live on Apathis, but ships from Io don't land there. Instead, they travel up an abridged and spinning elevator tether called a rotavator that we'll explain in a moment. Apathis also has an even shorter, non-spinning tether with a collector on the end of it that it uses to scoop up material it captures from volcanoes as it goes past. Normally on moons, we can't use a traditional space elevator. See our Lunar Space Elevators episode for the how and why of making that work. But because they are airless, we can run a long maglev track on the surface and get spaceships up to orbital speed before releasing them directly into space without rocket fuel. This is vastly more efficient, and even on moons with low gravity and no air, this helps us lower our cost to transport raw materials up from the surface by an order of magnitude. And it's no good for landings, and you can't aerobrake either. Still, it's great for moons. But the big ball of jello may not be a good place to be trying to run a 1,000-mile-long runway. Instead, let us imagine we hang a tether down from our space station, but hanging just off the ground, with a hook or attachment apparatus or even a pod on it. We include a winch on both ends to let us raise and lower the hook to compensate for changes in altitude or bulging in the moon or planet. This long hook flying through the sky, a skyhook, is much shorter than a space elevator, on an order of hundreds of miles, not tens of thousands, and thus can be made of relatively mundane materials, especially when hanging over a low-gravity moon. It is moving rather fast though, here on an order of a mile per second. If we could hook up at that speed to attach to it, we could then climb it, gaining a bit of speed as we go, as the Skyhook travels slower at its lower tip than at its top, both while circling the moon or planet in the same time. But the circumference of the circle the lower piece goes through is shorter, meaning it covers less distance over the same time and thus is going slower. By raising the station and lengthening the tether, we could slow its orbital period down, and thus slow down the speed the hook at the end traveled at. Though again, the hook might be a magnetic coupler or a big cargo pod, or some elaborate device for grabbing things moving at high speed. Instead though, let us imagine we hung a tether or rod out from our station both up and down. By the previous reasoning, anything higher than the station is now moving much faster, just as what's lower is going slower. And since the station is already at orbital speed, and orbital speed drops as you get further from a gravity well, that higher endpoint is moving faster than orbital speed and would give you quite a nice boost to go sailing out of orbital space, to another moon of Jupiter or even the wider solar system, and without spending any rocket fuel. And again, because gravity is low and the distance is relatively short, we can use conventional materials like Kevlar or even carbon steel for our tether, and if we could mass produce graphene, it could do even better. Since there's no air in the way causing drag though, we could take this a step further. It's quite a pain to make a connection while you're moving a mile per second, but if our tether was itself spinning in a big circle while it orbited that moon, and spinning at, say, a mile per second in the opposite direction, then when the hook spun down to the bottom of its circle, its speed would roughly cancel out, allowing a short moment at a predetermined place and time where you could just hop on without needing high-speed rendezvous efforts. When it spins back up to the top of that circle, your spin speed now adds rather than subtracts to that orbital speed, giving you a very large boost to the speed you fly off into space at. Alternatively, you could just slide up the tether to the station at its middle, or down from that station, or connect to the hook as you came in from space. This version of the Skyhook is called a rotovator, and we even have versions where a tether hangs from another tether, sometimes both spinning, sometimes just one spinning. See our Skyhooks episode for more details. Now, every time you use these devices, you are losing momentum because you're giving it to whatever ship or cargo pod you hooked. For that reason, you have to regenerate it, and it also helps if your hook is an order of magnitude more massive than what you're hooking, and preferably more, to give it a bigger momentum reservoir. Handily, the insane amount of radiation in the area of Io means anything you're putting up there has tons of mass in the form of very thick radiation shielding. Now, around Earth, a Skyhook can regenerate its momentum by what's called electrodynamic tethering, which is where you run current down a tether, presumably generated by having some solar panels connected to it, and that gives you a magnetic shove off Earth's own magnetic field, pushing it back up. You could also go down and generate electrical power by doing so if you wanted. Unfortunately, not many places have a big magnetic field. Skyhooks can't use this trick on Venus or Mars well, or our own moon. It wouldn't be great for Io too, except that Jupiter has a huge magnetic field, and you could just flick on your magnetic shove when it would push you away from Jupiter and up from Io. It is also very likely that any other moon that wouldn't allow a conventional mass driver or space tower on its surface, out in the wider galaxy, would be a big wobbling blob of jello for the same reason, a close orbit of a very large planet, and thus could probably use this trick too. You could extend several tethers out from the station, like spokes on a wheel, which would allow you to have more points of it touching with the ground per orbit, and also ensure you had a wire you could be electrodynamically tethering off of at all times. Another neat option might be to put a tire on that wheel, not just spokes, so that you could have a big spinning ring whose bottom was always at relative stop compared to the ground below. Given the nature of Io though, I think you might want to skip that option or keep the bottom of the wheel a good deal higher. On more stable moons or dwarf planets though, you might literally run that right over the surface so that it and its parent moon or planet look like a pair of connected cogs of gears. You would probably need to flatten that track out like a world-girdling highway or train track, but this would probably let you run whole trains up and down from the surface directly on that tether. That's an important notion too, because while we talk about wanting to mine asteroids and moons, we often lose track of the sheer scale of those bodies. It would take a few trillion trips by the average modern freight train to move the mass of Io, which would mean one per minute would take about 10 million years. Io would also be a good candidate for an orbital ring, assuming we have some decent magnetic shielding materials. An orbital ring works around any body that allows normal orbit. It's basically a spinning hoop turning around faster than orbital speed inside a non-spinning sheath whose combined angular momentum is just right to keep both in orbit. This gets you a big ring that isn't spinning or is spinning as fast as the planet or moon below is turning. We normally can tilt this at any angle we want, not just around the equator, by connecting tethers down to the ground to act as anchors against precession and as a means for moving people, power, and cargo to and from space. However, here we would probably need to keep it to the equator and not anchor those tethers, but just hang them down like the Skyhook, and they would be stationary relative to the ground since the ring they hang from is. You would probably need to be winching these up and down to keep up with the planet's surface rising and falling a couple hundred feet from the tides, but that should not be a problem and is something you would build into an orbital ring tether anyway. It's just a little more important on a place like Io and probably needs to be a bit more robust. We will call this equatorial orbital ring around Io Keroresa, who in mythology is Io and Jupiter's other child, their daughter and mother of Byzas, the legendary founder of Byzantium, later called Constantinople and now Istanbul. There really shouldn't be any problems with landing pads and smaller temporary structures on Io. It just isn't a great place to be contemplating mile-high arcologies or vast labyrinthine mining tunnel complexes. Definitely more the sort of place you strip mine, which for folks who don't know the term, outside of making environmentalists shudder, is a method of mining that involves removing the surface layers of soil and rock, called the overburden, to access underlying mineral deposits. This technique is commonly used for extracting coal, ores, and other resources located close to the Earth's surface, and often leaves huge patches of once beautiful land and ecosystems looking like a desolate hellhole. But as mentioned earlier, desolate hellhole already describes Io rather well. Alternatively, Io is rather pretty from space. All that brimstone, burned by demonic levels of radiation, gives a rather nice coloring. That radiation is a big deal and controls how you work and travel there. When discussing radiation, we have what's called the HVL, half-value layer, and that's the thickness of a given material that would cut the amount of radiation going through it in half. Double that thickness, and you get a quarter of the radiation, triple it, and an eighth. 10 HVL will get you about 1,000th, and 20 HVL a millionth. HVL is a bit of a ballpark figure, as it does vary by the type of radiation and the material. It is not unusual to give it in terms of X-rays or in terms of gamma rays of the 500 keV range, what gets released by a positron-electron annihilation, but any work well enough for our purpose today. Lead is well known for blocking radiation, and its HVL at the 500 keV gamma range is 0.4 centimeters, while the HVL for water at this energy is 7 centimeters. A few inches. Gamma rays are relatively easy to block. The radiation Io will hit lethal levels after a few hours. It's about 36 sieverts a day. Getting a single sievert is bad. We generally like people's lifetime exposure working with radiation at their job down under a sievert, though you could probably do more. Astronauts get about a dozen millisieverts a month. Now it's quite likely by the time we get out to Io for serious settlement, we'll have such amazing radiation and cancer treatments that you could be absorbing an entire sievert a month, not 100th of one, and be just fine doing that your whole life. But realistically, we want to be dropping Io's radiation downside habitats to less than 1,000th what it is, which would take at least 10 HVLO shielding, and even at short-term locations like a rover or shuttle, getting it down to 100th would be nice, which still takes 6 to 7 HVL. If your shielding HVL is a centimeter, that means 6 or 7 centimeters or about 3 inches of that shielding, which is a lot of weight for a car. Indeed, it's getting into the tank armor range. Space stations and surface habs can get away with using way more material, including cheap and easy but heavy options like water. You can use a meter of water in a honeycomb-like metal tank and you're good, and that's where you keep your excess water reserves. Dirt and regolith work well too, and down on the surface with low gravity, you can normally build pretty thick overhead because of that low gravity. We don't actually know how seismic Io is at a day-to-day level. We have never planted a seismometer there, and we probably need many years of data from many different locations to really be confident about construction possibilities. You could probably park a satellite with a good laser on it nearby to measure the wobble and estimate where that is on the Richter scale, but in the meantime, we should assume the worst, and that means rigid structures are not your friend, and neither are ones sticking several tons of regolith right over your very crushable skull. Inflatable structures might work, though the HVL of air is pretty large, and it might only be good enough if you had a large crater filled with the stuff and domed over. I should note that hydrogen, which is incredibly abundant out there, is actually a very good radiation shield. Helium's not bad either, so inflatables filled with pressurized hydrogen or helium might be viable. We could also consider giving it a thicker atmosphere of gases. It's cold enough to hold one, especially with some artificial magnetosphere tricks, and there's plenty of gas available. We could imagine a thick nitrogen atmosphere like Titan has, or an oxygen-nitrogen mix we could breathe, or something heavy in carbon dioxide or some other gas good at absorbing radiation. We could then have floating habitats, lighter than air or heavier than air ships, as there is an immense supply of hydrogen and helium right next door. Then you could avoid the entire problem of shifting and volatile surfaces. All in all, surface life down on Io is not a great option, and orbital life above is probably better, with teleoperated robots doing the mining and as much of the maintenance as possible. Same for smaller ships. Bigger is better under the square cube law, as a ship twice as wide would have 8 times the volume or mass on board, but only have 4 times the surface area to shield, so you could double the shielding thickness without proportionally increasing the shielding mass. So if you were shielded at 10 HVL, 1,000th of radiation gets through, and if you scaled your ship up by double, now you are at 20 HVL and only 1,000,000th of that gets through. This is why I always note that radiation issues on spaceships and stations is a modern era problem. Big ships sourcing their fuel from someplace that isn't a giant gravity well like Earth can economically move through space with meter-thick armor if need be, and something using a spacecraft drive better than chemical fuels similarly doesn't have as big a problem. If you want to be flying around Jupiter's orbital space, to include its moons, you don't actually need a very advanced spaceship, as it doesn't need a ton of delta V or to get the stress of high acceleration or speeds through atmospheres, but it does need good thick armor for the crew, and that likely means habitation areas for living and working are buried inside the ship, while any cargo that isn't particularly radiation sensitive is stored on the outer layer to protect you. That likely would include your ship's fuel and air and water reserves, not just bulk freight you are moving. Colonizing Io is also about colonizing the entire Jupiter region. It is very easy to move between those moons, but it's also a place where Aldrin cyclers are awesome. Aldrin cyclers are large spacecraft, even modified asteroids, that are on an elliptical orbit around the Sun that takes them past 2 planets, usually Earth and Mars, and passes close by both of them each orbit. They don't need any fuel to stay on that orbit once they are placed on it, so you can load them up with external shielding for the long trip, while shorter trips from the planet to them or them to the planet can be made in lightly armored and shielded shuttles and thus save fuel. This isn't limited to planets around the Sun though, it works just as well for 2 moons around a planet. Travel times tend to be similar to orbital times, as the cycler has a longer orbital period than either of the bodies it passes by, but spends most of it out beyond both of them. So you have personnel who presumably maintain them during the whole trip, but visitors just jump on for the relatively short trip between the 2 bodies, and you presumably have multiple cyclers running the circuit so that folks don't have to wait for the cycler they came on to return. Indeed, a cycler usually makes a fast trip from body A to body B and not from B to A, or does vice versa. Fast from B to A but not A to B, so you want to use them in pairs. Io's orbital period of just under 2 days is exactly half of Europa's, which is exactly half of Ganymede's at just over 7, as they are in resonant orbits, though Callisto, our 4th and most distant Galilean moon, is a bit more than double Ganymede's at 16.7 days. A Jovian cyclocraft, therefore, depending on which two moons it's on a circuit of, is doing that circuit on a timeline of a week to maybe a month. And an Io to Europa one is probably doing that phase of the trip in around a day. Jupiter has 95 moons at last count, including some closer to it than the Galileans. That number doesn't include the Trojan asteroids, which are quasi-satellites and has changed a bunch since I was a kid. Indeed, I think it's been different for every Jupiter-centered episode we've done over the years. Any two of them could have their own Jovian cycler, and most are well outside the intense radiation from Jupiter to the point that the thick glass of a dome would protect you from the radiation just fine. All of these would need some station keeping and probably could work out paths that took them close enough in distance and velocity to rendezvous with other bodies than just their chosen two, especially out at the deeper moons with their longer cycler periods. Some take years to orbit Jupiter. I'm probably not making Io sound like that awesome a place to live and work, but the typical person living out there probably lives in a rotating orbital habitat anyway, and wouldn't really notice the difference between that exterior having slightly thicker or thinner shielding on it. It's also a huge source of resources, and the awesome thing about Jupiter and its moons is that it's essentially its own micro-solar system. Not all that micro either, again ignoring the Sun, Jupiter outmasses everything else in our solar system combined. Those inner moons especially are just hours or days of flight time apart, even using modern rockets, the kind that need months or years to get us between planets. Think of Jupiter's moons as a rich archipelago in the ocean of our solar system, with Saturn and the other gas giants much the same but smaller. Io is one of the bigger and richer islands. It's just unlike most of our other metaphorical islands, it actually has the volcanoes and earthquakes common to island archipelagos on Earth. I should also note that Jupiter's radiation is something that a big civilization could do something about. For one thing, a large source of it is all the sulfur dioxide blasting off of Io. Io's plasma torus could be diminished by harvesting those blasts before they left Io, by the conceptual equivalent of lowering a collection hood over one from an orbital ring. That would help with the radiation problem near Io a lot. So too, a lot of that radiation is solar wind getting trapped in Jupiter's magnetic field, 20,000 times stronger than Earth's, and is akin to our Van Allen radiation belt but bigger and stronger. As we discussed in our looks at Earth's orbital infrastructure in a time further ahead, we might decide that we want to lower the radiation around Earth, or on other planets like Mars or Jupiter, by putting a large magnetic deflector at their L1 Lagrange point with the Sun. This isn't nearly as huge and energy intensive as people tend to assume, as we looked at in our episode on giving Mars a magnetosphere so it could better hold an atmosphere. It's already in the zone of technology we possess and power production we utilize, so it's a mega project, but not like trying to build a planet or something, which we'll get to momentarily. Tap those volcanoes and deflect that incoming solar wind, and the radiation around Jupiter will go down vastly. If you limit the amount of gas propellant you are shooting out of spaceships to velocities and trajectories that will take them out of Jupiter's gravity well, or down to Jupiter, and utilize a lot of non-propellant space travel options like tethers and cyclers, you could make Jupiter a pretty livable place. Indeed, that same L1 Lagrange point deflector could also include some thin but enormous lenses to pump more light out to the general area or target it on the individual moons. A Jupiter-sized lens might be no more massive than a medium-sized asteroid, of the kind we have tens of thousands of. Long-term, and with sufficient automation to provide your brute force, you might even opt to make Io a shell world, a big hollow planet-scale object full of compressed hydrogen and helium taken from Jupiter, which is 20,000 times more massive than Io. See our episode Megastructures Hollow Earth for engineering and other details, but you could actually make several Earth-sized planets out of Io that way, and the same for its siblings. Indeed, you could build all those artificial planets in their own big ring around Jupiter, a Kepler rosette, of easily a dozen Earth-sized planets at least. Those could be placed out by Callisto and given atmospheres to protect them from radiation, and you could prevent them tidally locking if you wanted. We talked about options like this in more detail in our episode on terraforming the moon. They are examples of our channel's motto for mega projects: If brute force isn't working, you're not using enough. Though if you cleared the radiation problem, you could stick them all even closer to Jupiter than Io is so they had a 24-hour day even if tidally locked. On Io, Jupiter is already 26 times wider and 1,300 times larger in surface than the Moon is in our sky, and would be even bigger on some artificial planet built closer. For Io, one side sees Jupiter never, always faced out from it, while the other sees it as an enormous presence all the time, when around 40 times brighter than our full Moon once you adjust for relative size and drop off in sunlight. That's not super bright, by the way. The sun at noon on Earth is 400,000 times brighter than the full Moon. On Io, that difference in Jupiter being bigger and then being further from the sun narrows that, but to a scale of 10,000 to 1 instead of 400,000 to 1, which is huge but still makes the sun brighter out there, even though it appears a tiny dot in the sky, smaller than we see it. And Jupiter would hang massive in Io's sky, and the skies of those other moons too, albeit smaller. Long solar eclipses would be very normal too, especially on Io. So, will we see a colonized Io? I think so. Though probably not one with lots of domed garden habitats down on its surface. Settlement comes in many forms, and on Io I think we'll see in the form of orbital rings and habitats hanging just over it, helping to mine Io's riches from above. A future of humanity in space is likely to be one in which the colonies around Jupiter feature far more immensely in our solar system than Mars or Venus, as against moons are like a mini solar system, and Io is likely to play a large role in that future. Albeit its exact role is a bit hard to say and likely to change and shift around as settlement near Jupiter progresses, but then given Io's mercurial nature, that seems rather appropriate. As we saw today, some places might be better colonized without lots of fragile people and structures, and that might be exactly the sort of situation where an artificial intelligence would be ideal for handling most maintenance and routine operations. In this month's Nebula exclusive, Caretaker AI and Genus Loci, we explore the concept of both AI wardens and even post-humans put in guardian roles over everything from a small facility or habitat to entire planets or interstellar communications or defenses. That's out now on Nebula, the largest creator-owned streaming service where we release a bonus episode every month, along with all our regular content a few days early and ad-free. Other bonus content and Nebula originals from an ever-growing pool of creators. Using my code IsaacArthur, you can get 40% off and join for about $3 a month, about the price of the drink or snack you've been enjoying during the episode. We also now have lifetime membership and gift cards available to let you share Nebula with friends and family. When you sign up at my link, go.nebula.tv/IsaacArthur, and use my code IsaacArthur, you not only get access to all the great stuff Nebula offers, like Caretaker AI and Genus Loci, you also be directly supporting the show. The National Space Society and the National Space Club and Foundation are seeking applicants and nominations for the Krista McAuliffe National Space Educator Award, honoring outstanding secondary school educators in space-related STEM fields. SFIA is proud to support the cause. The deadline to apply is November 30th, 2024. Teacher, astronaut, and Challenger crew member Krista McAuliffe embodied a passion for education and space exploration, and this award recognizes teachers who mentored, advised, and helped guide students towards space careers through participation in space-related competitions and professional activities. Recipients receive a $1,500 grant, travel expenses, accommodations, and recognition at the Goddard Memorial Dinner in Washington, D.C. Use the QR code or link in the episode description to learn more. So that's it for today, but join us this weekend for Sci-Fi Sunday on October 13th to explore the concept of mushroom-like extraterrestrials and fungal aliens. After that, we'll deep dive into the topic of ocean habitats on Earth and beyond on October 17th. Before looking at distant humanity and strange and even alien paths we might take in a distant post-human future. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show by becoming a member here on YouTube or Patreon, or check out other ways to help at isaacarthur.net. SFIA's episodes also come out early and ad-free on our streaming service Nebula, like this month's exclusive episode, Caretaker AI and Genus Loci, at go.nebula.tv/IsaacArthur. As always, thanks for watching and have a great week.